Hello everyone, my name is Vishal Deep. I'm a PhD student at Iowa State University. I will be presenting the paper Experimental Study of Life Cycle Management Protocols for Batteryless Intermittent Communication. Having batteries in conventional sensor node is one of the major hurdles in unleashing the full potential of ubiquitous IoT sensing. Battery lifetime is limited to the number of charging cycles. For non-rechargeable batteries, it is just one. Replacement is not always feasible and can be expensive. There are also environmental concerns due to chemicals used in the manufacturing and disposing of batteries. One of the most promising alternative to batteries is to use energy harvesting from ambient sources, such as solar or radio frequency, and store this energy into a small capacitive energy buffer that is using batteryless sensor nodes. For example, this is MSP430 microcontroller powered by harvesting RF energy onto a 50 millifarad capacitor. However, the energy consumption of microcontroller and radio devices can be higher than the harvested energy. Therefore, these devices operate intermittently. That is, it turns off completely when the capacitor reaches a voltage called off threshold that can no longer support operation and remains off until sufficient energy is available to have a voltage above on threshold that turns on the system. A single on time plus off time is what we call a life cycle of the node, and a life cycle ratio is the on time divided by on time plus off time. Due to intermittent operation and no control over harvesting rate, the off times are uncontrollable and unpredictable. The on times are usually short due to small energy store and limited harvested energy. That makes direct communication between these nodes extremely difficult because the nodes need to overlap their on times to have a successful communication. In the real world, successful communication are few and far between. The main goal of this work is to improve the probability of successful communication and thereby reducing the latency and increasing the throughput of communication in batteryless intermittently powered nodes. That in turn will make the communication more dependable in such nodes. More concretely, we need to minimize the TTO and increase the OPS, which are communication performance metrics for intermittently powered nodes. The TTO is the time to overlap. It is the time between successive instances of overlap. This metric, proxy for communication latencies, introduced by intermittency of the devices. Second is OPS. It is the amount of overlap per second. This metric is proxy for intermittencies constraint on throughput of the communication channel. The figure here shows the TTO and overlap in green of two intermittently powered nodes. The node A takes 2 life cycles to overlap with the node B in this example, but this could easily be a high number in real world scenario. Every on time without overlap is a failed opportunity for communication. We don't have a control over the harvesting rate of a node, but we do get to control when the device can turn off. In the previous work, we proposed lifecycle management protocols, LMPs, that leverage nodes' limited control over its lifecycle by early dying. There are several techniques that can be used to control it, but for this work, we use microcontroller to turn off the power regulator on RF harvester. By dying early, a node can save energy and can turn back on more quickly, as shown in this figure here, and thereby reducing the TTO. This technique can be used to align nodes on time with the other node. It keeps dying early until it does a handshake with the other node. And when there is a successful communication between the nodes, both nodes cancel early die and use the whole energy they have to communicate with each other in order to improve the throughput. Please note here that this technique does not change life cycle ratio, it changes period of life cycle. Unfortunately, reasoning about optimal values of on time in LMPs across harvested energy is challenging. Therefore, we develop models to analyze and identify optimal pairs of TTO and OPS for these stateless limps. On the x-axis of this contour plot, we have on time of node A in number of slots, where a slot is time discretized value of one successful communication, including acknowledgement reception. On y-axis, we have on times of node B. We can observe that the plot is symmetric across the diagonal. That means both nodes can be swapped and it does not matter which one is sending or receiving. The best performance can be seen at the upper left and lower right corners, where one node on time is minimum and other node on time is maximum. The OPS model plot is also symmetric across the diagonal, but the OPS is maximized when one node chooses minimum on time and other node chooses an on time of around 15 slots. To understand this, please note that a node with smaller on time overlap occurs at beginning. Therefore, it can expand its on time to max that allows more overlapping to happen, thereby having more throughput. The point at 15 slots optimally balances it. Another interesting prediction by models is that these optimal points stay fixed regardless of life cycle ratio. In this example, we have reduced the sender life cycle ratio to 1% and receiver life cycle ratio to 5.5%. Significantly lowering the life cycle ratio increase the TTO and decrease the OPS as seen on the scale in the figure. You can find more about the mathematical models in the paper. Okay, so these models provide interesting insights, but what do they mean practically? To find out, we implemented LMPs on the physical hardware. The figure shows a node that consists of a RF energy harvesting unit from PowerCast. The microcontroller can turn the power regulator off using reset pin on the harvester. It also has a 50 millifarad capacitor to store harvested energy. The main microcontroller board is MSP430 FR5994, which is powered directly from the harvester. This board does all the computation and LMP's decision making. The MSP430 board also has FRAM on board, that is a non-volatile memory with lower write latencies than flash, and it can be used to save volatile memory data before dying. The main controller board powers the CC1352 radio board and communicates with it using SPI. Both boards run TI RTOS. Radio board use TI's EasyLink radio driver, and it transmit or receive in sub 1 gigahertz range. The communication consists of a two-way handshake. The sender unicast a packet to the receiver, and the receiver responds with a software acknowledgement. Now let's understand the software implementation using an example. In the figure, node A is a sender node which is running LMP1 configuration, and node B is a receiver node which is running LMP2 configuration. In general, an LMPX configuration, the sender transmits X packets waiting for ACK after each packet transmission. If it does not receive an ACK after X packets, it early dies. That is, disables the energy harvester's voltage regulator. On the other hand, if the sender receives an ACK, it continues to communicate until it runs out of energy or times out. Correspondingly, the receiver running LMPX listens for X times 5 milliseconds to receive a packet from the sender. We empirically found out that 5 milliseconds is enough time to have a successful communication, including ACK reception. As the receiver successfully receives packet, it extends its listening time by 5 milliseconds until it runs out of energy. Otherwise, it disables its regulator. In this example here, as soon as sender turns on, it sends a single packet to the receiver. But the receiver was off at that moment, therefore it didn't send an ACK. Therefore, sender decides to early die. Same thing happens in the second and third life cycle of the sender. In the fourth life cycle, both sender and receiver are on at the same time. Therefore, in this iteration, when sender sends a packet, receiver replies with an ACK, and both nodes cancel early die and start communicating until they run out of energy. Let's find out what happens when one of the node dies while the other node is still communicating. Let's see what happens when the sender dies before receiver. Assuming both nodes are overlapped and successfully communicating initially, consider after the last successful communication, sender dies but receiver still has energy. So it waits for one more communication slot, but it does not receive a packet from the sender, therefore it dies to save the remaining energy. Similarly, in the case where receiver dies before the sender transmit a packet but never receive an ACK. Therefore, it turns off its power regulator to save energy. The complete experimental setup consists of two intermittently powered nodes running on RF harvested power. A USB powered sniffer node records the experiment statistics like number of packets transmitted, number of ACKs received, on times and off times of both the nodes. We evaluated the performance on different lifecycle ratios, which were initially set by manually tweaking the distance and orientation of RF transmitter with respect to RF harvester and observing lifecycle ratio on the oscilloscope. Each LMP configuration either run for 30 minutes if the lifecycle ratio is high or 120 minutes if the lifecycle ratio is relatively small. Now we compare the results we got experimentally with the results from models. Figure here shows the TTO as predicted by the model and TTH as measured by the experiments at select LMP configuration of 1, 5, 10, 15, and max. The TTH time to handshake is similar to TTO, but it also includes MAC and physical layer delays. The experimental results generally follow the trends predicted by the model. The best median TTH of 2.85 occurs at extreme asymmetry when one node uses LMP1 and other uses max LMP, since this increases the probability of on-times overlap. There's also a peak predicted by the model at 1.1 configuration, which can also be seen in the experimental results. Next figure shows the respective OPS and throughput for selected LMP configurations. As our model predicts, the lowest latency LMP combination 1 max does not match the highest throughput LMP combination, which is 115. This happened because the 1 max combination has a lower average overlap per on time, since the node running max LMP config on average has already consumed approximately half of its on-time energy by the time overlap occurs. This behavior is predicted by the model and can be seen here, where maximum throughput of 146.16 kilobyte per hour is observed when the sender does LMP15 and the receiver does LMP1 configuration. In conclusion, we proposed a generic framework for LMPs that can be used by research community to explore the design space. We provided formal metrics to evaluate the performance of communication in intermittently powered nodes. Then we developed analytical models and validated those using implementation on actual hardware. In future, we want to develop the communication protocols on top of this framework. We would like to extend the design to multi-node communication. Another interesting direction is exploring the design, modeling, and implementation of stateful LMPs that saves the off-time information in non-volatile memory, and that time information can be further used to facilitate the communication. The LMPs are not just for communication, it can be a part of comprehensive energy management solution, including sensing and computation for batteryless, intermittently powered devices. Thank you for listening. I'm looking forward for your questions.